Our next speaker is Shirin Enshaeifar, who's going to be giving an introduction to machine learning here, and hand over there.
Thank you, Mark.
So, Shirin, over to you.
Good morning, everyone. Welcome to the summer school at Surrey. I hope you're enjoying the nice and hot weather. So, as Mark introduced, I'm Shirin. I'm a senior research fellow in machine learning at Surrey, and I'll be covering the first half of the course for Introduction to Machine Learning. Before I go through any concepts, there is some background material if you are interested to learn more and learn about the theoretical aspects of machine learning. There are very good books from Kevin Murphy and also Christopher Bishop, which are really good for machine learning, and there is a very good book example for real world in terms of the application and the challenges, which is by Hendrik Brink and two other authors. Also, there are a couple of very good websites for online courses in machine learning, which you can see here. Generally, I introduce Coursera and Udemy to some of my students that want to start to machine learning, specifically if they want to go through the coding for real-time applications. So, what we will cover in the first half is in general, the concept of machine learning, and some terminologies within this field, and specifically why and when do we use machine learning in our life as scientists. Also, we will focus on the types of learning. I will focus on two specific ones which are very common, and then after that we look into the general pipeline of the machine learning, and I give some examples for specific tasks from pre-processing and feature extraction. So, first of all, the concept of machine learning. In 1959, there was an informal definition about machine learning, which is a field of study that gives computers the ability to learn without being explicitly programmed. And what that means is that some programs, you define every single step of that code. So you say, okay, if the value A is above this threshold, do this specifically, go to the next step. So you are defining all the steps specifically. But in machine learning, that's not as specific that you go. You give the data and the machine tries to learn the structure from that data itself. A more formal definition of machine learning is given by Tom Mitchell in 1988, which says machine learning is the study of algorithm that improves the performance at some task based on some experience. So in general, machine learning is that when we have some goals in mind, which is defined as task, for doing that, for analyzing those, we have some data, which they call it experience or E. We try to learn a model, and we are trying to improve our performance over time, and that's defined by P. So a well-defined learning algorithm always will have these three elements, P, T, and E. And it's important to define these three elements before you start writing, for example, a learning algorithm. So why do we use machine learning? There are so many reasons for that, but I focus on four main concepts and four main reasons. The first one is that we want to discover new knowledge from very large and very complex data sets. For example, imagine that based on the statistics in Google, they process 24 petabytes of data, which is 10 power of 15 bytes per day. In Facebook, there are about 10 million photos uploaded every hour. In YouTube, there is 1 hour video uploaded every second. And in Twitter, there are about 400 million tweets per day. So if you want to analyze them manually at the same time, it's just not possible. So we would require some learning algorithms to go through all of these data to give us some information about those. The other use for machine learning is when we want to analyze multimodal and unstructured data. So given the previous example, let's imagine that we want to analyze all the photos, the videos from YouTube, the text from Twitter, all at the same time. There are different modalities, and they're all in structured data. So what we want to use machine learning, for example, imagine that there is a news going on, and we want to see the correlation between all these different sources of media to realize something. And that's what machine learning can help us with. The other main use is when we want to provide customized or personalized models. For example, in biology, there are so many learning algorithms that they go through all the data, through the genomic data. But if they want to analyze DNA, which is unique per person, it's just not possible to do it manually. So they would require some learning algorithm to go through that for them. And the last one is to develop continuous and real-time solutions. For example, imagine that our sat-nav is providing our solution with the shortest path, or based on other criteria that we tell that to give us some path, and then we take a wrong exit. It suddenly needs to adapt itself. It needs to find where you are and give you the correct path again. So it has to be continuous, it has to be real-time, and that's, again, when machine learning can help us. So now that we know the concepts, there are many use cases that we face every day in life with machine learning. For example, when you upload a photo on Facebook, it detects the face, and sometimes it even recommends who that person is, so face detection and secondly, recognition. We have a lot of speech recognition around us, Google Home, Alexa, Siri on iPhone, so many different applications. We have recommender system, so if you've been using Amazon or Netflix, you can see that they come up with suggestions based on your history. In Netflix, it can, for example, even tell you how much it matches your previous history. Spam filtering, all of us use, so lots of our emails go either spam. Sometimes it makes a mistake, but generally it's okay. The other thing is clinical diagnosis for medical imaging. So when we have lots of X-ray and MRI and it detects tumors, for example. Again, that's another challenging point of machine learning because we can't 100% rely on the machine. So we always have to keep doctors in the field along with all of our algorithms. The other thing is fraud and unusual card transaction detection. So it might have happened to some of you going abroad using your card, receiving a text, is that you or not? That's an unusual transaction detection using a machine learning algorithm. And there are many more in finance, for example, for price prediction, in robotics, autonomous vehicles, and many other fields. These are just very daily examples, basically. So now that we know these examples, we will pick one of them to go through the concept of machine learning. So I mentioned about the task, about the performance, and about the experience or data. If we consider the spam filtering algorithm, first of all, before writing any algorithm, we need to define, okay, what is our data? Our data is the database of emails. Some of them might have been labeled with human labels to say, okay, this is spam, this is actually not spam. So that's our experience, that's our database. Our task is to identify a new coming email as a spam or not. And our performance is how well we are classifying that. So our algorithm will improve performance at this task using some of the data that is available to us. There's some basic terminologies always used in machine learning. I'll quickly go over them. So if we consider the same example for spam filtering, this will be something like the experience or the data set that you will have. Each row represents a sample, instance, or observation. They're all the same concept, it's just different terminologies. And our data, the size of the data, represents that how many samples we have. In each column, we have a property for each of those samples. For example, here we have a number of new recipients, email length, country IP, or customer type. So they are all property of every single sample. And what they call it is the input attributes or features. And what they mean by dimension is the number of these attributes. So the size is the number of samples, and dimension is the number of features. And every email, this is labeled data. We have an output label for it, and every email has a type, for example, human label data. And what this is called is target attributes or output. In machine learning, sometimes we don't use all the features that we have in place. Sometimes we don't use it as we have in place, so we do some pre-processing. And that means that we are changing the features. So we might start with this dimension, but after analyzing the features, we might come up with a new dimension. In some cases, we are trying to reducing them, and in some cases, we are even trying to increasing them. You'll see some examples later. The other terminology in machine learning is the model. A model tries to see all the input data and based on the properties, based on these features, try to say, okay, given that data, I think using this model, I can predict Y. So a model fit the data to predict your output. And for deriving a model, for evaluating it, generally you divide the data set that you have either in 2 data sets or 3 data sets. We start with 3. So they divide the data into training data, validation data, and test data. So majority of the data you pick up from your data set to learn the model that is out there. For example, here the yellow examples, sorry, some of them are kind of mixed between yellow and green. So majority of the data has been used as training data to learn a model to fit and say, okay, given these properties, when can I say this is spam or not? Then in some cases, you might see a validation data when a smaller set of data is used to optimize your learning model. So you have a learning model from your training data, then you try to optimize it, and another smaller set of group of data is called test data when you're trying to evaluate your algorithm to see, okay, given the model that I learned, is it doing good or not? But in some cases, in machine learning, they don't go for the validation. So they go only for training data and test data. Now that we know these concepts, let's go over some concepts of learning. Here I only focus on the 2 most common learning methods. There are some methods called supervised learning, where we have the data, the input attributes, and we also have a label for them. You have the output target for it. There are also some methods called unsupervised learning, when we have the samples, but there is no information regarding the output. We only have the input attributes. And there are some other methods, semi-supervised learning, which is a mixture of unsupervised and supervised method, and reinforcement learning, which are kind of more broad aspects of machine learning. So let's first see an examples of supervised learning. So as I mentioned, in this method, we have the given data, we have the input attributes as X, and for each sample, we also have the output attribute as Y. And the Y is kind of representing a model. So for every X, using a model of f of X, for example, here, it can predict the Y. And our goal is to learn a good approximation of this function. So basically, look at this example where it's for house pricing. So the feature, the input attribute is size of the house. And based on that, we have an output of, or the price, which is considered as Y. And these are the samples. So what we try to do is says, okay, we want an equation, we want a function to actually represent this relationship between them. One way to do that is to say, okay, I'm going for just a straight line. So I'm going to pick up here, go through there, which they are all mathematics, so you don't have to do it. It's just different learning algorithms. But let's say we just want to go with a straight line. And for example, if there is a new house with this size, I can estimate the price of the house using this model. But do you think this is a good model? How do we know that? Well, our goal is to develop a model that we get as good as we can and as close as we can to the actual value of our output. So for example, here, if you look at this example, the actual Y is here, is around 250. But within our model is even below 200. And that's what we call as distance metric. So for each Y, the actual value, we get the approximated value and we compare them to define a distance metric. And based on that, actually this is not that great. It could cost your customers lots of money for their house price, and that's something that you don't want to do. So what is a better approximation? For example, something like that. This is better. So every single sample is kind of closer to its estimated value, so the distance metric is improved, there's less distance or less deviation between the actual value and between the approximated value, which is cost function, which will be discussed with my colleague later in the second half of this session. So again, in the previous one, we defined a model. In this one, we define another model, which is quadratic. How do you decide? It's based on the learning algorithm. It's based on the distance metrics. But you don't have to do it all manually. It's just a learning algorithm that computers do that on its own, and it actually improves by more and more samples when you provide them. There is another case of supervised learning data. So in the previous examples, we saw that the output layer was a number, so it was a price. But in this one, the output layer, the example is for breast cancer. So you have a size of a tumor from, let's say, medical image analysis data, and an algorithm wants to decide, okay, is this a cancer or not? So it can only be yes or no. And that's the model that, at this stage, that's the model that actually represents what you're having in hand. So what's the main difference between this example and the previous one is that in this model, the output layer is categorized, is discrete value. And this is called classification. And when you have real number, when you have continuous data, when you're allowed to provide a continuous data for your output, that's regression. And both of them are subset of supervised learning models. Based on the data sets that we have, if we have labeled data, in medical cases, there are mostly classification problems, but in generally in finance, in prediction, in stock analysis, there are mostly regression algorithms. I mentioned about the X with, for example, brain tumor and breast tumor and the tumor size as the input feature. We don't have to stick to only one feature, because, for example, sometimes that's actually not enough to decide whether that's a breast cancer or not. So the size of the X, the dimension of the X can be more than one, and that's what we call features. So for example, for the breast cancer example, rather than tumor size, we can also look into the age, because that is actually relevant whether something is a breast cancer or not. So in this example, we have two features, and that's when we call the examples as multivariate or multidimensional. Not only the input, but also the output could be different values. It could be binary. It could be either it's a breast cancer or no, or it can be actually more than two. For example, you either say it's actually not a cancer, or you also want to define the type of that cancer. And in this case, you will have three labels, and that's what we call as multi-class problem. So it's either a binary or multi-class problem. I mentioned about fitting a model, and there is another terminology regarding the fitting that it's good to know. It's about underfitting and overfitting. It happens for both regression and classification. So if you look at the same model here, in the first example we said, okay, we're just going to go for a straight line. But based on what you see, this model is too simple to explain what is actually happening within the data. And that's what we call as underfitting. In terms of the terminology, they might say it's actually low in variance, or it's actually high in bias in the error of the modeling. And that's when we call it underfitting. On the opposite side, we can go for a very, very perfect model for our training. So we have a model that actually completely follow every single sample that we have in our training data. And when you look at it, you say, okay, perfect, that's great. However, the problem is that this is great only for your training data. So if you go for another sample, like right here, it wouldn't know anything about it. It cannot estimate the value. So you cannot really generalize this model. And this is what we call as overfitting or high variance model. It's kind of like, say, it's too perfect, it's too good to be true. So what we really want in machine learning is a balance between these two. So we want to estimate, okay, but we don't really want to go something that is too perfect or too simple. So these two examples are the appropriate models. Again, how you can decide it, it's based on distant matrix, it's based on validation algorithm using your test data, and that's actually why you use your test data. Otherwise, every algorithm, every training algorithm that would present something like that, it would be perfect. But when you test it on your test data set, you will know if it's actually overfitting or not. You can have a similar concept in terms of classification. So if you look at here, this is too simple, so it does not discriminate your labels. And this one goes like crazy, kind of curving around every single sample, even if it is in the group A, and it's too complex. So this kind of represents, again, appropriate model. So after knowing the concept of the supervised method, so what is the concept of unsupervised? As I mentioned, in supervised learning, we have the features, but we also know the output targets for them. So we say, okay, these are class A and these are class B. And what we are trying to do is to learn a model, and when a new sample is given, we want to say, okay, which class actually it goes to. However, for the unsupervised learning, there is no output. We only have the input attributes, so we don't know really what's going on within the data. For example, let's say you have so many contacts in your phones and you have so many texts in your phone. Those could be inputs, and you want to know, okay, which one is a family member, which one is a friend, how many groups are there? Is it family, friend, work colleague? Is it, I don't know, different groups of people from far, people from my trips. So you don't know first of all, you don't know how many groups out there. And second, you don't know who will belong to each group. So you only have the input, but you don't have any output. And for that, what you do is that you will give all the data to the machine and say, okay, look, this is the data. I don't know what's going on within that data. Try to learn a structure within that data for me, and try to categorize my data based on that structure that you will find. So for example, if we give that data to a machine, say, okay, I think there are two classes within this group, by saying I'm thinking, because there are also some ways to define that number or not to define that number actually. But for now, let's say, okay, I think there are two groups within that data set. I don't know who belongs to who. I don't know what's the structure. Try and learn the model within that data and categorize the people. And in this example, it categorizes it in two. Generally, the algorithm does it based on some, again, distance matrices. One of the very good examples of unsupervised learning is called clustering. So it's exactly the example that I gave you. So you give the data, it categorizes them into different groups without knowing any prior knowledge about who belongs to each group. There is another example of unsupervised learning, which is called anomaly detection. So you say, okay, here's my data. I don't know what's going on there, but try to give me what is very different from all the other samples. And one of the very good examples in business is the fraud detection or anomaly detection. And what algorithm tries to do is that to find a distribution, to find a model that represents all these in a very similar way, and try to find out, okay, what is the furthest way, the sample that is most different than all the other samples. And that's another example of unsupervised clustering. So now that we know about supervised and unsupervised learning, but generally, what do we do if we want to write a machine learning algorithm? Each of these elements could take days to even develop. But in general, there are one single flow for every machine learning pipeline. The first one, and for anything, you need to understand the domain. You need to have some prior knowledge. Okay, what is the data? What is the feature? What is the output that I'm looking for? What I want to do with it? And after knowing all those information, you will go through the data. So the data is collected. It could be from sensory data. It could be from phone. It could be from media, any sort of data. After that, you need to actually prepare the data. So not all the data looks very clean like the ones that we just saw in the examples. They could be missing data, they could be very noisy data. So you need to have proper pre-processing to make it ready to actually go through the model learning algorithm. And those learning could be supervised models, could be unsupervised models, could be reinforcement learning, could be neural network or deep learning, which you will see tomorrow. And after any learning model that you train, then you can go through the model validation to optimize your learning algorithm and also to test your algorithm. And when everything is good and when everything is in place, then you provide the analysis and you visualize the data to probably could be your customers, your patients, to whoever your front end user is. For now, let's go through some of the examples of pre-processing because that's one of the most important aspects of machine learning. So let's consider this example. In here, we have 3 input attributes as age, country, and salary. And let's imagine that we want to analyze this data. It doesn't matter if it's labeled or not labeled, and it doesn't matter what we want to do with it at this stage. All that we know is that we want to provide a learning algorithm on this data set. First of all, you might see that there are some missing examples here. So there are some cleaning process that you have to do before doing any sort of analysis. Secondly, these 2 features are numerical numbers. However, the middle one is categorical, is a text value. So how can you integrate all these features to go within one machine learning algorithm? Because algorithms are based on numerical analysis. So if they want to go with all of them, they have to be in the same sort of common data model. It could be all in text, it could be all in numbers, but it has to be common. That's what it matters. The other thing is that we need to split the data into training and test. And after that, we also need to do the feature scaling. And the reason for that is that even if we didn't have this second feature, these range between, let's say, 0 to 90, and these are about 10 power of 3. So, if we put it as it is into the learning algorithm, they will kind of ignore the effect of the age in the learning algorithm. So how are we dealing with all these problems? The first aspect is the missing data. So actually one of the most simple way for missing data and dealing with that is data imputation. So for every single feature, you replace the missing data with either mean or median. Again, this is one of the most simple way of data imputation. So for example, for here, I use the mean of these values to replace the missing values, and same for the salary values. There are some very good methods which works based on the distribution of the data. So it looks at the distribution of the data, and based on that distribution, it tries to actually predict what the missing value is out there. Okay, now we have all the values, but we want to integrate. So again, these are numerical data. This is categorical. So what do we do with that? One way is I would say, okay, there are 3 elements. There are 3 categories in this feature. Okay, I'm going to say France, I replace it with 0. Spain, I replace it with 1. And Germany, I replace it with 2. Can you guess what would be the problem with this method? Mm-hmm.
You can play some kind of order. Right. So
Yeah. Yeah, exactly. So you could say that, okay, it doesn't matter for me if something is France. It doesn't mean that France is smaller than Spain if I put France to 0 and Spain to 1. But machine doesn't understand that. So if you give that value to machines, it actually puts higher priority for the country that has the highest value. So that's called label encoder. So that's not good for doing it for your input feature when there are categorical data. But another way to do that is that you would replace this column, so you take that out and you replace it with 3 representation here. One replacing for France, one for Spain, and one for Germany. So for every country, if it's France, only the column of the France will have 1, the others will be 0. And in this way, the machine will know that, okay, there is no priority about the country, about the values, either just that country or not that country. And that's what is called as one-hot encoder, which is very much used within the machine learning when you want to integrate numerical and categorical data. There is one little point that if your output data was categorical, so if your label data was, okay, for example, spam or non-spam, and if you wanted to do that, you could use label encoder, because for output, you're either saying, the machine knows that you're either saying this is 1, this is 2, this is 3. So it knows that that's just a label, it's not a feature, it's not a property. So for your output, it's okay to use label encoder. But if you have ever input data, you cannot really use label encoder. You have to use one-hot encoder for machine learning to understand the relationship between these properties. Okay, so we covered the missing data and the integration. The other problem is that we want to split the data into training and test data, right? So say, okay, for example, look at here. I select majority of the data as my training set. Normally it's around 80%, and I choose the rest of the data as my test set, for example, 20%. Again, the problem is that you could randomly select an 80%, which is very good, which represents all the different variations that you want to see within the data, but in some cases you might miss it. In some cases you select randomly an 80%, which does not really represent all the samples, specifically if you have rare samples within your data. So to overcome that problem, what you do is that you go through the training a couple of times, and that's what we call as cross-validation process. So if this is your samples and this is your data sets for the training data, first you go for the first 20% as a test data and select the rest as the training. In the second process, you go for the middle 20%, and you will just go on. So you basically shift your test data and your training data. And if, for example, you look at here, if you go for 20% test and 80% training and just keep switching it, that would be 5-fold cross-validation. Again, something like that is just, say, one line of code in machine learning that say, okay, this is my data. I want to do 5-fold cross-validation, give me a training and test data, and it just does it for you. So now we did all the grouping for training and test data. The other thing is that if you look at here, again, as I mentioned, values are between 0 and 1 for the 3 middle features. For this one is between, let's say, 0 to 90. For these one are huge. So you don't want to integrate them yet, because the problem is that you are kind of ignoring the effect of very small numbers. So that's why you go for feature scaling, to kind of change the scale of every single feature. You can do it either through standardization or normalization, and you do that for every single feature. And here you can do it through through every single feature, and you can see the values. There is some other technique for machine learning, for pre-processing, which is called feature extraction and feature selection. Or sometimes you might have heard about dimensionality reduction problem. And what you do is that you look at the data, and it doesn't comply for this data set, by the way. But you look at the features of the data and you decide, actually, you know what? The features that I have in place, it doesn't tell me much. So I need to do some other algorithms before I even give it to my machine learning algorithm as a features. And that's some sort of algorithms. You might have 3-dimensional features. You might reduce it to 2D. Actually, I have a very good examples I can show it to you here. So for this, for dimensionality reduction, it's very useful, and in general it could be feature selection. So you tell your algorithm, okay, among all the features that I have, select the ones that give me the most information about my purpose of algorithm. For example, one of them in terms of the dimensionality reduction is reducing from 3D to 2D. However, you have to remember that it's sometimes very tricky, because dimensionality reduction could mislead your algorithm. And this is one of the very good examples from Eamon. So this is a 2D representation of a 3D environment. So if you reduce that 3D into 2D, you are completely misleading your algorithm. So you have to be very careful about this, the use of this algorithm and how it can actually affect your learning algorithm. Okay. So we did all these pre-processing steps. Now all the data is ready. What we want to do is that we want to give that to our learning algorithm, either supervised or unsupervised, to learn a model, then test it, and then decide to which algorithm I can be using it for, and provide the analysis. Regarding the examples for specific learning, in terms of mathematical examples, in terms of loss function and distance metrics that I measure, I can pass it to my colleague. But before that, I think it's good to know that what we covered in terms of the machine learning. So it's general concept and it's general use cases. The terminologies in terms of the data, size, model, dimension. In particular, be careful with the use of size and dimension, because that's mostly when some confusion happens when you, for example, talk to some people not from the field of machine learning. Also in terms of the features, which are input attributes, and a label, which is the output attribute, and the concept of training and validation and tests, or cross-validation algorithm, as I mentioned the example. The learning model, which could be supervised or unsupervised, and the concept of distance metric, and underfitting, and in general the pipeline of the machine learning, which includes a lot of pre-processing steps. And I will now pass it to my colleague to go over for the second half of this course.